Right, good morning, everyone. Right, we are almost done with our topic on Loci, right, that is with regards to the chems. Right, but today we want to look at a new concept in terms of motion. We want to look at simple harmonic motion. We want to look at uniform acceleration and retardation, but we still want to continue with our roller follower. So we are going to explain as we do the exercises or the task, how the simple harmonic motion would work compared to uniform velocity. But in simple terms, you find that with regards to uniform velocity, this is a type of motion that would start, if it is at 100 kilometers per hour, it will start at 100 kilometers per hour, then and end at 100 kilometers per hour, which sometimes may not be applicable or favorable to machines. Right, you need something that would generate momentum as it goes. Right, so you need to pick speed from the start, then you gain speed, then when you reach the end, you reduce your speed. Right, that is defined by what we refer to as simple harmonic motion. So, like I said, we have already looked at the type of followers, right? That is the wedge-shaped, right? Which can also be referred to as a needle-shaped or a point, right? Then we also looked at the type of follower, the roller, right? We have basically have got the wedge-shaped, which is a needle-shaped or a point follower. Then the other one is a roller follower. Right, then these are the most common used, okay? You will still find that we have got a flat-shaped follower, but we are not going into detail with regards to that. But the most ones which are commonly used are the wedge-shaped or the needle-shaped or the point-shaped follower or the roller follower. Now, types of motion, like I've already explained, we have got uniform velocity, which is constant velocity. From start to finish, the speed is basically the same in a particular direction. Then we have got simple harmonic motion. Right, with simple harmonic motion, you find that you have got a gradual gain in terms of speed. Then when you are somewhere in the middle, the speed is at its optimum. Right, then when you about to reach your end part, the speed is reduced. This kind of motion is also perfected by what we refer to as uniform acceleration and uniform retardation, okay? So this one would take into consideration that there's very little circumstances where you would start with the same speed and end with the same speed. So there has to be gradual gain in terms of momentum and gradual slowing down in terms of that momentum. That would define what we refer to as simple harmonic motion as well as uniform acceleration and retardation. Big terms, but simple to understand in terms of drawing. Then we have got action of the follower. How does the follower work, okay, with regards to the chem profile itself? When the chem turns through one motion cycle, that is one revolution, remember we always divide the cycle into 12 equal parts, and that is a cycle. The follower executes a series of events consisting of rises, right, dwells and returns. Rise is the motion of the follower away from the chem sender. Dwell is the motion during which the follower is at rest. So it can be said to be dwelling. It can be said to be at rest. It can be said to be stationary. It is one and the same thing. And return is the motion of the follower towards the chem sender. The other term that can be used in place of return is fall. So when the follower is falling, right, it is moving towards the camshaft sender or the chem sender. Right, let us look at the construction of all these. Now that we have got two new motions that we want to illustrate as to how they are used in chem profiles. As always, remember, I hear and I forget, I see and I remember, I do and I understand. Most importantly, I want you to do it in order to understand what we are doing right now. So please make sure you pay attention where you have got questions. Don't be hesitant. Throw those questions right away so that we can respond to them. Thank you and enjoy the lesson. Right, given information, a roller follower for a disk came in its starting position. Right, so we have got the starting position with regards to the roller follower. The minimum distance from the camshaft center to the cam profile. Right, the minimum distance from the camshaft center to the cam profile. Remember, the cam profile will start on the underside of the roller, okay, is equal to 16 millimeters. So let's check if this is 16 millimeters. There you go, it's 16 millimeters. So once you have gotten that 16 millimeters, you stand at the center. Touching the underside like this, and then you draw a circle, but it may not be outlined just like that. It's fine, that's a mark. Right, then the camshaft diameter is 16 as well. So we measure radius 8. Sorry about that. Right, so that is the camshaft. Now, once you have drawn the camshaft, the next thing that you want to do, right, you want to hatch that. Not so clear. There you go. All right, so that is the minimum diameter, right? That is the lowest the follower would fall in terms of contact with the cam. Right, then we have got the camshaft. Right, normally you find that the camshaft is connected to the cam itself by way of a key so that they are able to turn at one time or simultaneously. Then we also need to consider the direction. Here it says anti-clockwise. Draw something like that. You can just darken one end like that. It shows the direction, okay? Now, as you can see what I've done, right, I haven't even looked at the rest of the question. I've just looked at the information that is given with regards to the specifications and worked on that because that is critical. This is putting everything in perspective, right, so that you You know where you are starting from and you know where you are going from there. Now let us look at the motion. The motion says the movement of a disk cam showing simple harmonic motion and uniform acceleration and retardation. From 0 to 180, the follower rises with simple harmonic motion to a height of 56. Right, so I'm going to do this. Draw a line like that. Right, then measure from here to there, 56. The 56 will give us now the maximum diameter. But once we have gotten this, of course, you can draw another line like that. Right, so the space in between here, from here to there, that would give you the maximum displacement. Right? 180 to 360, the follower returns to its original position with uniform acceleration and retardation motion. So if it rises with simple harmonic motion, it falls with uniform acceleration and retardation. Like I said, when we look at simple harmonic motion, we are looking at the gradual gain in terms of speed with regards to the movement of a follower. Then when it reaches the peak or the top end or the bottom part, right, it sort of reduces the speed so that it lands without a thud, okay? Right, so there isn't an abrupt start and an abrupt end. It is gradual. That is key with regards to uniform acceleration and retardation, with regards to simple harmonic and simple harmonic motion as well. Right, so we have now measured from here to there, which is 56. We can now draw the maximum diameter. Stand at the center of the cam profile. Right, then draw a faint circle like this. Right, and even divide the circle into 12 equal parts. Faintly. So there you go. Those are the divisions. All right. So this is the starting position. So we can say this is 0, which is also 360 degrees. Right. It's moving in an anti-clockwise direction. So the first one, which is 30, so that it will be the first to the line of action. That's 30 degrees. Right. So then from there, you have got 90 degrees, 180 degrees, 270 back to 360, but this is just not 330 degrees like that. So that is the representation of the information on the cam side. Now we want now to look at the length of the displacement graph. The length of the displacement graph. Using a horizontal scale of 30 degrees is equal to 7 millimeters and a displacement scale of 1:1. Draw the displacement graph for the given motion, label the displacement graph and include the scale, project and draw the cam profile from the displacement graph, show the direction of rotation, we've already done that. On the cam profile, H the shaft, we have already done that. Like I said, that should be routine. The moment you have defined the camshaft, H it. The moment you have defined the minimum diameter as well as the camshaft, show the direction in between. show all the necessary constructions. Right, so we need to calculate here. Right, we are told that 30 degrees is equal to 7 millimeters. Right, what about 320? Right, if it is a complete cycle, 360 rather, right? We don't know about that. Then we take this one by simple proportion, that will be more, 360 over 80 degrees multiplied by the equivalent in terms of 30 degrees, which is 7 millimeters. Right, that would give us, if we calculate, 360 divided by 30 multiplied by 7, which would give us 84, right? That's 84 millimeters. That is the length of the displacement graph. So I'm going to measure. Right, when you measure, make sure you leave space on the left-hand side and also space on the right-hand side. This is important for the drawing of the simple harmonic motion as well as the uniform acceleration and retardation. So I'm going to measure here. That's 84. There you go. Right, so this is the box which will house the graph that we are supposed to define. Right, remember you are not supposed to outline, but make it as clear as possible so that everyone will be able to see. So the distance from here to there, that's 84. Then you can divide the 84 into 12 equal parts, the same number of divisions that you have on the maximum diameter. Right, so I'm going to draw a line. Right, at intervals of 5 millimeters. Remember, this construction is important so that you get 1 mark or half a mark, depending on the marking scheme, with regards to the division of the length of the displacement graph. Then you can draw the vertical projections. There you go, okay? You can label. Right, this is 0, right? That's 30, 60, 90, 120, 150, 180, right, degrees. Then 210, 240, 270, 300, 330, then you have got 360. The highlight of the motion. That's what you represent there. Right, okay. Now, we are told that from 0 to 180, the follower rises with simple harmonic motion to a height of 56. This is the height of 56. Right, and if it's going to rise with simple harmonic motion, all right, we are going to create a semicircle here. The semicircle and divide it into a number of divisions, which is 1, 2, 3, 4, 5, and 6. So let's find the center. Right, 56, that's 28. We'll still require this, so let's take it all the way to the line of action. Right, you stand there. Open to one end, check with the other end, that's fine. Then draw a semicircle like this. The next thing is to divide the semicircle into the number of divisions from here to there. If you don't have an even number of divisions, you can subdivide. Let's suppose you have got 5 from here to there, but you want to divide this one also into an even number of divisions. You can divide this one, say, into 4. The 5 which are already there, you can divide them again here into 4 or into 6. Right, so we have got this. There you go. Right. So those are the divisions, right? The same number of divisions which are from here to there, they are also inserted there. Right. We said that this is 0, which is our starting point. So you can say this is 30 degrees, this is 60 degrees, 90 degrees, 120, right, and 150 degrees, and this would give you 180. Right, so if we move right, if we move from here, we go to 30, right, that's 60, that's 90, 120, 150, and 180. So the 180 and the 180 automatically will be here, right? But let's do it systematically. Right, we know that from here to there, that's 30 degrees. So we project from here. We shall require this. So I'm going to take this one all the way. Right, so 30 degrees and 30 degrees, we have got a point there. We shall require this later. That's 60 degrees. That's 60 and 60. That's 90 and 90, which is here, all the way to the line of action. This is 120, from 90, 120, and 120 is here. That's 150, right? Then it will take us to 180. Then you connect these points. Like that. There you go. Right. We have got now the gradual gain in terms of speed. So speed is gained, or momentum is gained. Then there's a gradual slowing down towards the end like that. Whereas with regards to uniform velocity, the assumption is that from the start to the end, the speed is the same. It's constant, it doesn't change. So we can outline this. Right. So that's simple harmonic motion, which is based on a semicircle. Okay. Let us look now at uniform acceleration and retardation. Right. So you find that when you accelerate, you are gaining speed. When you retard, you are slowing down that speed. Okay. Right. So with uniform acceleration, you also count how many divisions do you have from here to there. Those are the same number of divisions that you are going to create. So we have got 6 divisions. So let's create a line. Let's create a line like this. Right. You divide this one also into 6 equal divisions. And I'm going to say 1, 2, 3, 4, 5, and 6. Connect this one to there. Right, remember it's easy to say 56 divided by 6 if it would give you an exact answer. No, it won't. So the graphical method would be the ideal one, okay, in terms of finding those divisions. Right, you take your straight edge. There you go. Right. So you have got the divisions 1, 2, 3, 4, 5, and 6, which is equal to the same number of divisions from the last point, which is 1, 2, 3, 4, 5, and 6 as well. But we know that this, right? We can even write here, this is 180, which is here. This is 210. This is 240. This is 270. That's 300, and that's 330, okay? Right, so these divisions are taken to the halfway mark, right? So you need to project this. 1, 2, 3 to this line, like that. That's 210, that's 240, 270 is already there. That's 300 and 330. Right, so it's 1, 2, 3, which is the midpoint, 1, 2, 3 as well. So you'll find that you would get a mark for the division and the projection from here to that, okay? Once you have done that, we can see now this is 180, this is also 180, so that point would always be there, all right? Now, if you are dealing with uniform acceleration and retardation, right, I will explain that one later, but this is what you need to do, right? The first line that you would draw without hesitation, right, is the connection from the start to the end like that. That line, as you can see, it would automatically pass through the sender. Right. Lines which are here, or points which are here, they are connected to the top. and points which are here, they are connected to the bottom. Right, so this is 240. If we could just 210, that's 240. If we could just illustrate that, this is 270, that's 300, 330. Right, so a line that I'm going to draw from here, which is 210, should also cut a line, a vertical projection for 210. So if I do this, there is a point which is being established, which is that point, okay? That is the point of the curve. Then you do the same. But this is 240. I should also cut line 240, which is here. That is the point of the curve. Right, then I go to 270, which is 270. I connect like that. You see, right, there is just a straight line from the top to the bottom, okay, or from the top to the bottom, or from the bottom to the top via the 270 and the 270. So that's also a point here. Right, then now I cannot project from there because I've already defined this straight line. So you would go to the other end. This is 300. Should also cut the vertical line 300 somewhere, right? Which is here. That's the point that we want. Right, then I go to 330. Should also cut the line 330, the vertical one. Like that, which is this point, okay? So you have got 180, 210, 240, 270, 300, and 330. Right, you connect these points faintly first. And do this, all right? Right, you'd find that the curve that you produce, right, it's similar to the uniform, the simple harmonic motion, but this one is more refined, okay? Right, so there's a gradual takeoff and there's a gradual landing off, which is smooth. So it's not going to be abrupt, right? It's smooth taking off, it's smooth landing, okay? In terms of the movement of the follower. I'm going to use a different color so that we are able to see the difference between the two curves. There you go. Right, so this is our uniform acceleration and retardation. Right, you start, then you gain speed, you accelerate. As you go or come towards the end, then you reduce your speed, that's retarding, okay? Once you have done that, the next thing is to label. Let's label our displacement graph. Always do that because there are marks for that. Provide guidelines for presentation of work. Your label here. That's our displacement graph. Then you write rotation in degrees. 30 degrees is equal to 7 millimeters. Then you indicate here displacement in millimeters or displacement 1:1. It's one and the same thing. Right, so that's your displacement graph, which is now in place. The next thing that you want now to do, all right, once we have defined the displacement graph, right, you project now from these points, each and every point as you go up, and each and every point as you go down to the line of action, which is this one. Already I have got projections for the rise that is moving from the camshaft center, right? Then I would do the projections for the fall, right, which is moving towards the camshaft center, right? So this one is 30 degrees. Then you describe an arc like that. That is basically the center. That's 60 degrees. That's 90. Let me push this one slightly. Right. That's 120 center. That's 150. 180 is already there. Now, the next thing, you take the radius from the roller itself. Take this radius like that. Right, at each and every point that we've described, it's either a complete circle like that or just a small little circle. That's for 60. That's 90. 120. 150. 180. Okay. Once you have done that, you connect using your free hands, the underside. Draw a tangential line. Like simply touching, but not getting into. So in terms of the rise, we have got this. Right. Let us now define by projection the points from the form. Okay. Right. I'm going to project from here. Right. That's 210. 240, 270 is already there. That's 300. And 330. Let me start with the 330. Let's describe an arc. That's 330. Right, that's 300. These are the centers. That's 270. That's 240. And last, that's 210. You take the size of the roller again. Right, you stand at the established centers. Just a faint, a faint circle. Like that, it's enough. But you come here as well. Right, then you also do the same. There you go. Take your pencil. All right, simply touch. There you go. So you now have got the profile in terms of the cam. So what is left now is simply to outline. All right, let me use a different color so that we are able to project. Here. When you want to rest, you can stop there. Right, you continue. It has to be a smooth curve. There you go. You now have got your cam disc. Right, last but not least, you need to label. Right, label. This is your cam disc. Like that. So this is it, boys and girls. Right, as you can see, right, from what we have done so far, right, it would appear with the term simple harmonic motion, uniform acceleration, and retardation. Those would sound as big words, but in reality, right, it's just a type of motion that is applicable to the cam construction, right, which is meant to make sure that you have got a smooth movement in terms of the cam itself, right? It's going to, the follower is going to have a defined movement, right, touching almost every part of the cam. Whereas when it is uniform velocity, right, you'll find that there are certain parts, especially if you are using a roller follower, which cannot be touched by the follower. And as such, you'd find that in terms of the performance of your machine or your system, it may not be that accurate, okay? But with regards to uniform, simple harmonic motion and uniform retardation, but it is now shown with regards to the cam disc itself like that. But we are going to do another exercise, right, which would make use of this same concept, uniform acceleration and uniform retardation. I'm going to explain less now. I'm just going to do it so that you will be able to follow the steps that we have done so far. And I hope you enjoy what we are doing right now. Right, so this is our second task. All right, as you can see, there are similarities, but the performance would differ. Right, a roller follower for a disc cam in its starting position. We have got the starting position as defined. The minimum distance from the camshaft center to the cam profile is 16, which is the distance from here to there, should be 16. Right, the camshaft diameter is 16 as well, just like we had with the previous one, and it's still, all right. We are going to make it a clockwise motion, right, just to change the direction. The movement of the disc cam showing simple harmonic motion and uniform acceleration and retardation, 0 to 120. The follower rises with simple harmonic motion to a height of 56. Then 120 to 360, the follower returns to its original position with uniform acceleration and retardation. Okay. Using a horizontal scale of 30 degrees is equal to 7 millimeters and a displacement scale of 1:1. Right, we know from our previous exercise that if it is 30 to equal to 7, the total length of the displacement graph would be 84. Label the displacement graph and include the scale. Project and draw a cam profile from the displacement graph. That's what we want to show. Show the direction of rotation on the cam profile, H the cam profile. So let's start with the information that is given. We are talking about the minimum distance, right? Which is, it's just to verify, it should be 16. Yes, it is, right? So we draw. We draw a faint circle like that. There you go. Then 16 is the camshaft diameter. So radius 8, we measure 8. I prefer you measure, then draw through that measurement. Then you can outline this at once, like that. Once you have done that, you hatch that part. When possible, always hatch with a 45 degrees set screen. Always hatch with a 45 degrees set square. Then from there you define the direction. But just for interest sake, we are going to change the direction to be clockwise. Darken this end like that. That would give you the direction. Right, okay. We know in terms of our displacement graph, it would always start from the center line or the center line of the follower or the roller, right? Unlike when it is uniform, it's a wedge shaped, it will start from here, okay? Right. It's a rise of 56, all right, for the first 120 degrees. So let's measure 56. The moment you do that, the moment you have measured that, all right, there is need for you to draw the line. This would give us the total displacement or the maximum displacement. Then from here, there you go. So that is the maximum diameter. Once you understand the concept with regards to curves, you'll find that it is very easy to do and to apply. Divide the maximum diameter into 12 equal parts. Like that. Right. So this is our 0, right, which is also equal to 360 degrees. Right, it's going clockwise, so our first point would be 30 degrees this side. Then we have got 90. We have got 180 degrees, 270, like that. Okay, right, so we are done with this part. Now let's focus on the displacement graph. Let's focus on the displacement graph. We have already said that the length of the displacement graph is 84, using the information from the previous exercise. So we come here. And make this one slightly darker than a construction line, but not as dark as an outline. There you go. Right, divide this one into 12 equal parts, the same number of divisions which are here. All right, so there you go. Right, so we are going to label here, that's 0 degrees, 30, 60, 90, and 120 degrees. Then we have got 360 degrees. Like that, those are the highlights. in terms of the motion. Right. So from here to there, right, the follower is going to assume uniform and simple harmonic motion. Then from here to there, it's uniform acceleration and retardation. Remember, if it is simple harmonic motion, it's a semicircle. But let's measure halfway through, which is 28. We shall need this, so we project it all the way, then draw a semicircle. This point is our center. There you go. Now, the next thing that you want to check, right? How many divisions do you have from here to, from this point to that point? It's 4. So you should also have 4 divisions. So if there are 4 divisions, all right, for 180 degrees like that. So each division should assume how many degrees? Right, so you can do that, right, at 45, you would have 4 divisions. So I'm going to do this. Such that we have got 30, 60, 90, and 120. That's 30, 60, 90, and 120. We can label that. This is 30 degrees, though we have divided by 45 degrees, but in terms of the graduations, it's 0 to 30, then 60 degrees, 90 degrees, then 120 degrees, like that. Such that if you project from here, you would meet, right? That's 60, that's 90, 120. So ultimately, we'll find that our next point will be there. So let's project from here to the line of action. It's already there. To the line of action like that. Right, this is 0. It's 10, 0. Then 30 degrees, it's here. 60 degrees. Then 90 and 90 is here. Okay. Right, you connect these points. Let's correct this one. Okay. Then we can outline right from here. Like that. So that's our simple harmonic motion, right from here to there through to 120 degrees. Right, that's our simple harmonic motion. So you've got 30 and 30, you've got 60 and 60, you've got 90 and 90, we've got 120 and 120, like that. The next thing that you want now, you have got how many divisions? 1, 2, 3, 4, 5, 6, 7, 8. So you also need 8 divisions this side. Right, sometimes there's a mark for this. So you create a line. Divide this one into 8 equal parts. We're going to use the actual 8. So we've got 1, 2, 3, 4, 5, 6, 7, and 8. This is connected to the last point. Like that. Take your two set squares or a set square plus a straight edge. Align with the end line. It's 150, 180, 210, 70, 40, 70, 300, and 330, like that. I can label here, right? This is 120 still, right? And that's 150, 180, 210 degrees, 240, 270, 300, 330, then to 360. Right, these divisions are projected now halfway, right? The number of divisions, so you 1, 2, 3, 4, right? We need to project all these divisions to that. Just for clarity, let me use a different. So it's 1, 2, 3, 4. This one is already there. Just like we explained with the last exercise. Right, the moment you have got the starting point and the end point, you can connect. It would automatically pass through that center or that point. Right, the points which are here should be connected to the top. The points which are below here should be connected to the other end like this. So I'm going to say this one. There you go. Right, okay, so this is 150 and 150 would meet here. That's a point that we want. Right, then this is 180 and 180. That's a point. Then 210 and 210. That's a point. But 240 and 240, the point is already there. Then we go to the other side. Right, so this is 270 and 270. We need it here. Then 300 here. Then 300. We need it there. Then 330 and 330, which is here. Okay. But we connected these points faintly. Then if we are satisfied, we can outline. I'm going to use the red pen again. There you go. Right. So that is uniform acceleration and retardation. When you start, you gain speed, and when you come to the end, you slow down. Okay. Now, once you have done that, the next thing now is to project. We've already projected from the simple harmonic motion. Right. So you take your compass now, like this. Right. This is for 30 degrees. Remember, we change the direction, which is 30. But the answer would still be the same. That's 60. That's 90. 120 is already there. Then you take the radius of the roller follower, take it from here, stand on the new centers that you have defined, and just draw a faint articulate circle, like that. So now, then through to 120. There you go. You can take your pencil. And we stop there. Now we need to project from here. That is 150. 180. 210. 240 is already there. 270. 300. 330. Start with the loss, which is our 330. The swing, that's 330. That's 300. 270. 240. 210. So let's go to that. 180. 80. 50. Okay. Then you take the same radius of the roller. This is 330. That's 300. 270. 240. 210. 180. And 150. Like that. Take your pencil. Go. Right, so that is the profile with regards to the chem itself, the chem disk. Right, so the next thing that you would need to do is to simply outline. Right, you outline that profile. There you go. But you can start on the other side. There you go. Right, so that is our chem disk. So you'd find that the roller is able to touch each and every profile of that chem disk. Right, then from there you need to outline by defining the label. Right, chem disk, like that. Right, so this is it, boys and girls. We have touched at two scenarios, right, all displaying the application of simple harmonic motion as well as uniform acceleration and retardation. I hope you have understood the concept, and we now want to conclude our discussion by applying from a past exam paper and see how this is also taken in context with regards to examinations. So let's look at now at a past exam paper. If we still have time, we look at two scenarios of that. Then we consolidate our understanding on simple harmonic motion as well as uniform acceleration and retardation. Right, this is a question on the chem, right, from a past exam paper, and to be specific, right, it's from 2018 paper. So let me just take this one up. Question number 2, like this, 2018, November 2018, so that if you want to practice on your own, right? We are not going to look at this. This is for another day, but we are going to look at the chem, right? Remember question 2, right? You could have a combination of the chem and the mechanism. Remember, the mechanism is also part of loci, so we are going to look at that as well. Right, let's look at this. Note, answer questions 2.1 and 2.2 for you to complete question number 2. Chem. A chem rotates at constant velocity, imparting the following motion of to a follower. It rises with uniform motion for 21 millimeters over the first 60 degrees. There is a dwell period for the next 75 degrees. It rises with uniform motion again for a further 43 millimeters over the next 45 degrees. It descends with single harmonic motion back to the original position over the rest of the rotation. Draw to a rotational horizontal scale of 360 degrees is equal to 114 millimeters. That is the scale, and a displacement scale of 1:1, the complete displacement graph for the required motion. Label the displacement graph and include the scale. So here what is required is basically to draw a displacement graph. And I think it's an interesting exercise for us. Now that we know the types of motion, the 3 main types of motion that are applicable in the chem construction. Right, okay. Now, the length of the graph is 114. Right, what is key here? Right, we need, first of all, to establish the total displacement. Right, we know that for the first 60 degrees, right, if we have got a picture like this, right, having divided this one into 12 equal parts, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, like that. You have got these divisions. I'm just sketching so that we have got a picture of what we are supposed to do. Right, okay. So if we say this is 0.0, this will be 360 degrees. Right, so for the first 60 degrees, that's 30 and 60 degrees would be here. Right, it rises 21 millimeters. Right, 21, let's suppose it's here. Right, so you connect, you have got something like that. Then there is a dwell for the next 75 degrees, so it's not going to rise, it's not going to fall, it's basically maintaining the same height. So if it is 75, we have got from here, that's 30, that's 60. So in between, you come here, you have got 75, but you are not going to say 75, you are going to say now, this is 90, this is 20, which is 130, 135 degrees, okay? So that's 135. So there's a dwell up to there, right? Then it further rises, right, over the next 45 degrees for 43 millimeters, right? So this is 50 plus 30, which means we are going to do this. Then you have got, it descends or it falls, right? So from here, it's going to fall up to 300 and what? 360 degrees. So we need something like this, right? This is what you need to do in terms of your understanding. You sketch, get the understanding, right? So from here to there, it rises uniform velocity, right? From here to there, it dwells for 75 degrees, then it rises further for 43 millimeters, but then it descends with uniform velocity, which is the semicircle like that. with simple harmonic motion, right, which is a semicircle like that. So let's look at it. The total rise, right, is going to be 21 plus 43, which would give us that's 64 from here to there. That is very important, right? The displacement, the length is already given, right? From here to there, we need 114, okay? The total rise is 64, right? Then 100 and what? 114. So let's look at the space that we have, right? The first thing that we want to check, right, is the height of 64, right? Somewhere there, that's fine. We are covered. So I'm going to draw a faint horizontal line like that. Measure. But measure from here to there, 114, that's 100, that's 110, that's 114, which is there, okay? Draw this one. Then consider now the total rise. We say it's 43 plus 21, which would give you 64. Here. So this is the first step. You can make this one slightly darker than the construction line, but just to give it a bit of impetus. Slightly darker. Not very dark. You don't want to confuse with the graph that you are going to make. Then the next thing is to divide this one into 12 equal parts. Finally, I'm going to use the actual 12 divisions. So that's 1, 2, 3, 4. Connect this one to the ends. There you go. Take your teaspoon. Right, so this is 0 degrees, right? For the first 60 degrees, that's 30 and 60, like that. Then 75, so 30, 60, we need 15 degrees, Right, that's 30, 60, and 75. You simply miter this, the 45 degrees, then we check this one up. So you would have divided this one into 12 equal parts. Let me just check some. Okay, slightly skewed. Right, okay. Then you are going to write here 135. Right, then $45, if we have got, that's 150, 90, 120, 150, 180, right, which is the 45, which is here. Right, then the end part would be 360 degrees. So you need these highlights in terms for you to be able to consider the graph. Now, we are told that the first 60 degrees, the follower rises with uniform velocity for 21 millimeters. So you go to the 60 degree mark, then indicate the 21 millimeters like that. You connect them to the start because it's uniform velocity. All right, then you do this. You project like that. That's for the dwell. It's not rising, it's not falling. So from 60 to 135 degrees, which is 30, 60, and 75, right? It's dwelling, it's resting, it's stationary, it's not rising. Right, then it rises with uniform motion for a further 43 millimeters over the next 45 degrees. So we have got 15 plus 30, that's 45, which means it comes here. Just want to show you that it's very easy to get these marks when you are dealing with curves. Right, okay. Then it descends with simple harmonic motion back to the original position over the rest of the rotation. This is where you need to check how many divisions left. It's 1, 2, 3, 4, 5, and 6. So you need to draw a semicircle, right? Which is divided into 6 equal parts. Right. The height is 64. But so half the height would be, but half the height would be diameter or radius 32. So we are going to do this. Copy to this point. Let's check also. That's perfect. Draw a semicircle like that. Right. Divide the semicircle into the number of divisions, or equal to the number of divisions which are here. In this case, there are 6. So we have got that. So this is 180, right? Just to give it, this is still 180. So I'm going to write 180 there, right? This is 210, 240, 270, 300 degrees, 330 degrees, up until you reach 360. Right. So the 180 and the 180 will still be there. Then 210, we draw a line like that. This is 210 and 210, 240. You have got that. This is 240 and 240, then 270, which is this one, 300, 330. So we have got this point, that point, that point, that point, that point. These are the points on the graph. Then you connect these points. Faintly first. So that's our simple harmonic motion. Once we have done that, you then need to outline. You need to outline from here to there, from here to there, and from here to there. Then you close that one. I'm going to outline. That's the dwell. That's a feather rise. Then you complete this one. There you go. But you have got the simple harmonic motion, okay? Right, last but not least is to label the displacement graph. Right, remember on the left-hand side, or even on the right-hand side, on the side, right, you write displacement in millimeters, okay? Or displacement scale 1:1. But you also check. Normally you'd find that the key labels, right, is labeling that displacement graph. If it is 1 millimeter, one mark like this, so you need to label displacement graph. You also need to label the scale. But if it is 2 marks, you need this. You need the displacement graph to label displacement graph. You need rotation in what? You also need the scale. So that will be half, 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 half in terms of the labels. Right? So I'm going to do all of them such that you would look at the marking scheme, displacement, graph, okay? Then you also come here, you write rotation, in degrees, and the scale is 360 degrees is equal to 114 millimeters, like that. Right, you'll be done. You will be certain that you'll get those 11 marks. Right, so next time we meet, we are also going to consider the lower part, which is about the mechanism. By then, I think we would have completed that task, okay? Right, we still have got a few minutes, so we want to look at another scenario, again from a past exam paper, and see how you'll be able to handle that. So this is now the application part of what you would do in CAPS in terms of understanding in terms of application, in terms of you being able to utilize the ideas that we generated. Right. Not so clean a paper in terms of photocopy. I think we'll be able to see. Right, okay. We want to look at the lower part, which is our chem. Right, the chem. The bottom left corner, the bottom left, given the bottom left, which is 0 degrees, starting position of the displacement graph on the answer sheet. Right, the follower rises with uniform motion for 15 millimeters over the first 30 degrees. There is a dwell period for the next 15 degrees. The follower rises with simple harmonic motion for 65 millimeters over the next 135 degrees to the maximum displacement of 80 millimeters. Right, if you check, you have got your first rise of 15 millimeters plus the 15. You would find that the maximum displacement would be 80. So what we need to do, right, let's project like this. We know that the maximum displacement is 80, so we can actually measure 80 this side. And we project like this. There is a dwell period for the next 90 degrees. After the total rise, the follower returns with uniform acceleration and retardation to the original position. Draw to scale 1:1 and draw to a displacement scale 1:1, that is on the in terms of the height, we've already factored that, which is 80. Then a horizontal scale of 360 degrees, which is equal to 180. So we need this to measure from here. No. So these are typical exam questions. Close there. So this is the box 4 for our displacement graph. Remember, once you have done that, you divide this one into 12 equal parts. We use the actual divisions 1 to 12. There you go. Take this one up. There you go. Right, we can label. That's 0. Right, let's look at the highlight of our labels. Right, the follower rises with uniform velocity for 15 millimeters over the first 30. So we are going to say 30 degrees. Then there's a dwell for the next 15 degrees. So we need to bisect this. That's take this one up. So from here to there, that's 15 degrees. Right, the follower rises with single harmonic motion for 65 over 135 degrees. Right, okay. So first of all, let's measure from here to there, 15. That's 15 millimeters. Then there's a dwell, right, like that. We connect this faintly, what's that? Like that, okay. Then that's the uniform velocity. Then there's a dwell up to this point. Then it rises, right, for 65 millimeters over the next 135 degrees. Right, 135, this is 30, 60, 90, 120, plus 15, right, which would give us what? 135. So that's 30, 60, 90, 120, 150, and 180. Right, so 60, 90, 120, 150, 180, which is here. This would give us, that's 30, 60, 90, 120 plus 15, that's 135, okay? Right, so if we look at this from here to there, right, we need at least 4 or at least 6 divisions, okay? Right, so I'm going to say, have this one, this is 65, but it's not an even number, so what I will do is, I'm going to miter this, so that we are able to get to the center. Like this. There you go. And you project it like this. So at this point, that's where we want our semicircle. Looks like I projected from a different point. Which is this point, which is halfway. Then slightly long. Draw a semicircle like this. There you go. Right. So this is 45. Let's divide this one into 6 equal divisions. keep making the same mistake, using the wrong point. But as long as these are construction lines, do not run to erase and so forth, unless you find that you are totally confusing yourself. Okay, so we need these ones like that. Right, so at this point, that's 45 degrees, right, 45, right? If we were to put this into perspective, you'd find that plus 30, that's 75, right, up until we get to 180 degrees, okay? Right, so we also need to divide this one from here to there into 6 equal parts as well. So we are going to disregard the divisions which are already there. That's 1, 2, take them here. Right, I spoke about this earlier, that sometimes you need to create, right, auxiliary divisions that would help you to come up with a graph. Right, let's take these ones down as well. This is in line. Let me use a different color. Right, so we have got 6 divisions here. So this will be our point 0 in terms of our divisions. Then we have got point 1, then 2, 3, 4, 5, and 6. But you connect this. Like that. But you connect from here to there like that. Right, that is part of our curve. Right, then we now need this one, which is 1, 2, 3, 4, 5, and 6. That is for the uniform acceleration and retardation. Right, there are 6 divisions. We are going to connect from here to there. It's not going to change. Like that. We divide this one into 6 equal parts, but we don't have space. So we are going to do this like this. Right, into 6 equal parts. That's 1, 2, 3, 4, 5, 8, 6. The last one is connected to here. We don't have space to draw it on the outside. Right, you count 1, 2, 3, which is the halfway. All these projections would be taken to the halfway mark. Which is one and the same thing. Right. The next thing that you want, you connect this one to the start. That's a point that we want. That's another point. The other one is already there. Then you switch on to the other end, which is a point. There is a point. You connect these points faintly. Now you have got your uniform acceleration and retardation. Let me start by outlining this. Like that. Then also this one. Like that. Then we have got the start, which is the dwell. Right, like that. I didn't want to look at this part where it says dwell for the 90, but I just wanted to highlight the concept of the simple harmonic motion as well as the uniform retardation. So this part, we skip this one just to make sure that we highlighted that which we want to show in terms of the motions that we are looking at. So from here to there, that's uniform acceleration and retardation. Right, I did not forget about this. I just wanted you to apply the concept of uniform acceleration and retardation, and also looking at simple harmonic motion. Even if you are not given the starting position, you can generate your own points getting down like that. The same number of divisions which are here should also be the same number of divisions which are there. Right, the next thing that you want to do, right, is to label displacement graph. And you can also write here displacement in millimeters, like that. And at the bottom, right, rotation in degrees. Then you also have got the scale, which is 360 is equal to 180 degrees. Remember, I removed the dwell at the top just to make sure that you are able to see clearly the application of the uniform acceleration and retardation. Right. There you go, boys and girls. I hope you enjoyed this lesson as much as I did. And when we meet each other again, right, I'm going to look at a complete question, right, for question number 2, where we start in terms of the displacement graph, right, coming up with the curve itself, right, which is a projection from the displacement graph. Not only the displacement graph, but all the way from the displacement graph to the construction of the curve. And in particular, we are going to look at question number 2 of 2019, November 2019. So if you have it, I want you to get hold of that so that as we do, as I demonstrate, you are also able to do it on your own. Thank you. Enjoy the rest of the day. Bye.